Good afternoon, ladies and gentlemen, and welcome to the Graduate Seminar Series. This afternoon, we have the pleasure to have with us Professor Robert Davis, who obtained his PhD degree in chemical engineering from Stanford University in 1989. He subsequently worked as a postdoc research fellow in the chemistry department at the University of Nabu in Belgium. He joined the faculty in chemical engineering at the University of Virginia in 1990, and he's currently the William Mean Thornton Professor. Professor Davis also served as chair of the chemical engineering at the University of Virginia from 2002 to 2011. He received the Wilhelm Award of the AICHE, the Emmett Award of the North American Catalysis Society, and the NSF Young Investigator Award, the DuPont Young Professor Award, the Union Carbide Innovation Recognition Award, and the UVA Rodman Scholar Award for Excellence in Teaching. Professor Davis has served as president of the Southeastern Catalysis Society, chair of 2006 Gordon Research Conference on Catalysis, chair of Catalysis Programming at the AICHE, chair of a U.S. government panel charged with worldwide assessment of catalysis by nanostructural materials, director of the Catalysis and Reaction Engineering Division of the AICHE, director of the North American Catalysis Society, co-chair of the International Catalysis Workshop in China, member of the advisory board of the International Conference on Solid Acid and Base Catalysis, and member of the editorial boards of the Journal of Catalysis, Applied Catalysis A and B, Molecular Catalysis, ChemCat-Chem, and ACS Catalysis. I'm so glad to have with us Professor Davis. Thank you very much for accepting our invitation. And now, without any further ado, I hand it to you.
All right. Thank you very much for that overly generous introduction, I would say. All right. So my screen is showing, correct?
Yeah.
All right. So today I'd like to tell you about a story of a research project that lasted for 10 years, which in the United States is a very long time for one single project to go. But I was fortunate to be a part of a large group activity in the conversion of renewable biomass. And so I'm going to tell you a few bits of that story dealing with alcohol and acid conversion over catalytic materials. So to kind of set the scene, this is a slide that I borrowed from Dow Chemical, and it just shows you why our activity was not focused on fuels, but was focused on chemicals. So realize that this left-hand bar is essentially how much distillate is being produced. And notice the magnitude of the y-axis. There's a break in it. So the distillate is essentially fuel. And then chemicals from hydrocarbons, okay. You can see olefins, these are the largest chemicals produced. You can see ethylene and propane and ethane and naphtha. These are much, much smaller than the amount of hydrocarbon used for fuels, okay. So again, look at the y-axis, there's two breaks in here. And you can see why in the US we started looking at conversion of seed oil, which is shown over here, because it's on the same scale, but using seed oil for fuel, obviously there's a huge mismatch. But corn as a carbon source is not too bad. You can see that we clearly have enough corn to look at production of chemicals, but again, not fuels, it's chemicals. So our center then focused on converting biomass to chemicals only. Now, if we look at the chemical industry, which was really developed around hydrocarbons, the composition of coal is carbon with a little bit of hydrogen. Oil, which essentially is, I just show a representative molecule because that's the main one in petroleum or gasoline. That's isooctane. That's CH2 roughly is the ratio. And then natural gas, the U.S. is moving toward the use of a lot of natural gas because of fracking. That has 4 hydrogens per carbon. So fossil carbon comes with hydrogen, but biomass carbon is essentially an oxygen along with the carbon and the hydrogen. So the carbon-hydrogen ratio is the same as oil, but way too much oxygen for our chemical supply. So you can see where what we're going to do is really manipulate oxygen in these things. So this is now pre-pandemic, which means I have no idea how many of these companies are still existing. They may be gone, a bunch, but at least a few years ago, a large number of small and large companies were involved in converting biomass to chemicals. And so these are not fuels, these are all chemicals, right? And so our Center for Biorenewable Chemicals, and that's what the symbol up here in the upper right is, it was a National Science Foundation center that was actually based in the center of the country at Iowa State University, and we were one of the participating universities at Virginia, was focusing on biomass to chemicals, but clearly the supply chain is a very long chain, right? There's the growing and harvesting of biomass. There's the conversion of it to sugars. There's fermentation of sugars. There's chemical intermediates, and then final products. And so our center really focused in green right here, which is the center known as Seaberg, is taking carbohydrates or sugars to chemical intermediates. So that was the part of the value chain that we focused our technology. And here's the classic question. What does biology do best, and what does chemistry do best, right? And so this has been an argument that's been ongoing for the entire life of our center, and it's still going to be ongoing, because if you talk to the biologists in their meetings at professional societies, they say we can do everything with biology or biochemistry or biocatalysis. And then you talk to the chemists and they can say, oh, we don't need biology. You tell us what transformation you want, we can do everything with chemistry. So the center had to wrestle with what is the best approach. Do you take a building block and use biology to make an intermediate, or do you use chemistry? And our approach was, let's just try to use the best of both worlds, right? And so we had various platforms, which was converting carboxylic acids using biology, that's the B, to diversify those, and then take the intermediate that comes from bio and use chemical catalysis to make the chemical precursors for the product stream. We had another test bed on pyrones and bifunctional molecules, again, starting with biology. And then in the pyrone case, it was using chemistry to diversify rather than biology. And then in bifunctionals, using both biology and chemistry to do diversification. So that was the paradigm of our center. So just keep that in mind. This argument is still going on. Is it better to use one or the other, or a combined approach of biology and chemistry to convert biomass? All right, so this all came from the analogy of how the chemical industry came from or petroleum discovery, right? If we think about a tree where the trunk essentially is our hydrocarbon resource, oil or natural gas, we then take the alkanes and cycloalkanes and aromatics and diversify it to the chemicals that we use for making all of our materials and paints and solvents and so on. And so that's the approach that the chemical industry used, is to use the hydrocarbon resource as the trunk. Well, we can think of now starch or cellulose, the carbohydrate fraction or the cellulose fraction of biomass as the trunk, depolymerize it to sugars, and then what can we do with that? And so you can see we can use a variety of methods to go up the tree and have the leaves as being the diversified compounds. And I'm going to talk today about diacids and dialcohols, but we were looking at all of these others as platform chemicals, the intermediates from the feedstock to the final products. All right, so the other thing one has to realize that the problem is always money, right? Because we're an engineering research center, not basic science. So we're trying to use the fundamentals of basic science, but to do something useful for society. And so this is the reality we faced all the time, is that the volume of a chemical is inversely related to the price of that chemical. So if you look out here in the bottom right, there's ethylene. And I showed you that there's a huge amount of ethylene produced from fossil resources. And the cost per ton is extremely low. And ethanol is the same way. And then as we get to very, very low, essentially the x-axis at zero, near zero, the value goes way up, but the volume is extremely low. So if we just blow that region up, that's what this plot in the upper right hand is, you can see now 1,5 diols, 1,6 hexane diol, and then there's adipic acid, which is the diacid, the 6 carbon. So here are the chemicals that you can make from biomass, but the volumes are really, really low. Okay, so these we thought are the targets because we're trying to say, can we work on higher value materials than fuels, which would be essentially so cheap, they have to be cheap enough to burn. Now we're trying to add value. The problem is, again, there's always a problem, right? Look at 1,6 hexane diol where my highlighter is, and here's adipic acid. So the diol and the adipic acid are simply analogs of each other. One's the alcohol, one's the acid, and the prices are very close. So you're changing pricing on the value chain depending on what the economic conditions are at the time. So when we started, one component was more expensive than the other, and then actually in the life of our center, they actually flipped in price. So it's really hard to predict what to do when you're down in this range of pricing with volume. All right, so with that as an intro, we're trying to manipulate oxygen with hydrocarbon backbones, right? Why? Because biomass has a huge amount of oxygen relative to the chemicals that we want. So petroleum, we oxyfunctionalize. Biomass, we have to manipulate the oxygen down. And so understanding how to move oxygen in and out of molecules was a main basis of our activities in the center. So I'm going to talk about 3 little stories about alcohol oxidation. Okay, so here we're trying to go up to an acid from an alcohol. I mean, this could be simply, ethanol to acetic acid. That's a process, right? And we can get ethanol from fermentation. Now, alcohol reduction, taking the oxygen out. All right, this is important, right? If you have a sugar, you want to deoxygenate it to get rid of all the oxygen that's involved in sugars. And then acid reduction, so this is the opposite of alcohol oxidation, is going backwards and going down to alcohols. And that depends on the value of the molecules you're starting with and ending with. So those are the 3 probe reactions I want to tell you about catalytically. And so now I want to just kind of give you some snapshots and then delve into some of the science to show our approach and where we're going in the future in this area. So I mentioned 1,6 hexane diol as a precursor to adipic acid. And why is that important? Because that's the dicarboxylic acid used to make nylon. Okay, so people thought, all right, if we can ferment maybe, and the biologists claim they can always make something and get straight to the final product, but you can also start from the alcohol and go to the acid. So we wanted to manipulate alcohols to acids, and we spent a lot of time looking at metal catalysts. All right, now just for definitions for the non-catalysis people in the audience. So we're going to define a specific rate. So this is right out of your reaction engineering class, where we take the mole change with respect to time and normalize it by something. And if you normalize it by the catalyst mass, then it's moles per second per gram of catalyst. Now, we like to use a turnover frequency, which means we're normalizing the reaction rate by the number of active sites, okay? And how do we know what those active sites are? In many cases we do, but in many cases we don't. But for platinum, if this 2 nanometer size platinum particle has half the atoms at the surface, we assume that those surface platinum atoms are the active sites. And we can count those, okay? And so here's a table that shows a bunch of data. These are platinum on carbon catalysts, different kinds of carbons, and different dispersions, which means that the particle diameters are different from 1.8 up to 6 nanometers. And look at the turnover frequency of this. The reaction rate is invariant on all of that. All right, so if you just plot the dispersion, which is related to the size of the metal particle, with the turnover frequency to oxidize that 1,6 hexane diol, we see that it's completely independent of the particle size. So it scales very nicely with the number of active sites on the surface. And we studied that reaction quite a bit. It does deactivate with time, and we mapped out all of the kinetics and of the reaction, including the oxidation of alcohols to intermediate aldehydes and side reactions of decarbonylation that poison the catalyst. So we did all this and we published it, but platinum itself is pretty darn expensive. Okay, so what we were really thinking about is how can we move away from platinum? I mean, engineers are always thinking platinum works great, and it does work great for about everything, which is why it works in fuel cells, it works in a lot of chemical catalysis, but look at the Earth's abundance of platinum is what you're seeing on the y-axis here relative to silicon atoms in the Earth's crust. That's what this shows, where you have per 10 to the 6th silicon. Platinum is down here in terms of rarity with gold and iridium, and it's extremely expensive because of that. So it's catalytically wonderful, but it's outrageously expensive. And so one of the goals of modern catalysis research is, can we use Earth-abundant elements and modify the environment around it to try to get it to behave much more like platinum behaves, right? Or some of these other rare metals, these transition metals. And so there's this interesting field of, fuel cells that it's all over the world right now, trying to replace platinum as the catalyst for the fuel cell electrodes. And so we've been watching this field pretty closely. And I just took this picture out of a science article. It's not our group, it's somebody else's, but I like the picture. And it's been reported over the last decade or so that if you put iron atoms in carbon or graphene sheets, and these sheets have defects where there's nitrogen defects, and that's what those little blue dots are, nitrogen atoms. And the iron sits in there, atomically dispersed, and it's thought that that is an active site for the oxygen reduction reaction, which is important for fuel cells, right? The H2O2, reaction or other reactions with oxygen. So reducing dioxygen is an extremely important fuel cell reaction, but it's also critical when we oxidize hydrocarbons. We are using O2 as a reagent. So we said, how about trying these things for catalysis, not just the oxygen reduction reaction for fuel cells? So we teamed up with some people that were doing the fuel cell work, and we said, could we have some of these materials? And here we have, this just is a schematic representation of a graphene sheet, but it's actually a high surface area activated carbon with nitrogen defects in it. And these were synthesized with a bunch of different types of atoms, chromium and iron and cobalt, and nickel and copper, for example. And we did some model alcohol oxidations, and that's what you're seeing, say benzyl alcohol or some others. And we probed that, and we reported that in 2017 that these things do work. So I just want to show you, though, how good they work or how well they don't work. Okay, so the turnover frequency now is this TOF is defined relative to the number of these isolated atoms. So there's the iron-doped nitrogen carbon has a turnover frequency of 0.78 times 10 to the minus 3 per second for benzyl alcohol oxidation, which is pretty bad because platinum on carbon, which is what I showed you about, we spent a lot of time on, is orders of magnitude more active per platinum. Now, granted, iron is as cheap as dirt, right? It's essentially in dirt. But platinum is so much more expensive, you could say, well, maybe that's worth the trade-off, but there's a lot of reaction engineering issues if the catalyst is not very active. But we did notice copper tend to be much more active than iron. And so when we were probing the chemistry of this, we put deuterium on the molecule, and that's what you're showing over here, is to show that the kinetic isotope effect using a deuterated alcohol compared to a non-deuterated alcohol is severe. It's very big with iron, which means iron is great for fuel cells. It can do oxygen reduction reactions, but it's really having trouble breaking the carbon-hydrogen bond, which is part of our chemistry that's not involved in the fuel cell, right? So now we had to consider not just the oxygen reduction reaction, but breaking of carbon-hydrogen bonds, that the activation of carbon-hydrogen. That's what that kinetic isotope effect was. Well, we found that the copper was better than iron, but cobalt was even better. And so this just shows you now the kinetic isotope effect for breaking the carbon-hydrogen bond during alcohol oxidation is identical to that, or it's not identical, but much closer to that of platinum. So it's like, oh, okay. So now we see the rates are better. The kinetic isotope effects are starting to look like platinum. The question is, how many active sites are really in there? These catalysts are kind of hard to make. You essentially put a bunch of stuff together in a flask, dry it out, heat it up, and decompose it all and hope it all goes together. I mean, that's not the most elegant way to make something, but these are pyrolytic processes that are many, many hundreds of degrees C to form these things. And so the question is, what's the active site? So we learned how to make this, and we had a big campaign in the lab with at least 3 different people working every day, making new materials, optimizing the conditions to try to do this. So I just show you 2 micrographs. I hope it shows up online, but these are dark field images of cobalt and copper atoms in the high surface area activated carbons that are doped with the nitrogen. So everywhere you see a light dot, and look at the scale bar, that's 2 nanometers or 20 angstroms. So a single light dot is essentially a single metal atom, and it's in a dark field, which means the heavy atom shows up as a light part of this. Now, you can see kind of in the background the curvature of the carbon sheets, right? So this is an activated carbon, and so you can actually see the structure of the carbon as the curved sheets move around, okay? And so cobalt and copper are shown in these 2. Yeah. Now, what's the structure around these? Okay, so now it becomes a material science interrogation. What do you actually make when you just heat this stuff up with all these precursors with nitrogen? We use dicyandiamide, we use metal nitrates, we use activated carbons, and lots of optimization of conditions, which is all trial and error, to be honest. And so we went to a synchrotron to probe the local structure using a technique that's called X-ray absorption spectroscopy. And what this does is measure an absorption coefficient in the X-ray region that involves the excitation of a core level electron, and that excitation is an absorption event. And that's what's shown right here. And the XANES is the near edge part of the spectrum. And then you have these wiggles out here that's related to the structure around the absorbing atom. So what this means is we can tune to the element that we want to investigate. So here we've tuned to the absorption of cobalt. There's the absorption edge of cobalt. And then we can do these all in the presence of different gases and different temperatures, because X-rays can go right through the windows. We can do actual chemistry while interrogating with X-rays. If we do a Fourier analysis on these wiggles, we can actually get what's called a radial distribution function, which shows you how many nearest neighbors are right around those atoms, okay? And sometimes you can even get information on the atom type. But our analysis says, okay, there is the distance uncorrected by phase shift of the cobalt to the nitrogen atoms in the defect, okay? And we can do this analysis, and we think there's about 4, which, okay, it looks like it's sitting in that defect on average. And then there was this shoulder out here. We actually had no idea what this was when we were originally doing this. We were trying to find the oxidation state of the cobalt, and here's the here's the near edge spectra, a bunch of model compounds like phenanthroline and phthalocyanines. And unfortunately, these are all supposed to be relatively similar to cobalt-2, meaning that except for cobalt metal, which is cobalt foil. And so the edge positions were all over the place. So this was the problem with trying to use this to get the oxidation state of cobalt. So we did some XPS, X-ray photoelectron spectroscopy, and looking at the satellite peaks associated with cobalt-2 and cobalt-3. So again, it was a lot of material science work that we did that essentially says we think we have evidence now for cobalt 2+ sitting in these sites surrounded by nitrogen in that plane. Okay, now that's the majority of the sites. Is that all of them? Who knows, right? If you go back, who knows where these are? They all the same? It's hard to believe that everything would come out uniform at the end, right? So let's keep going and say that can we treat this in temperature and different gases and see what happens? We've ramped up our cobalt catalyst at 373 Kelvin all the way to 750 Kelvin and saw essentially no change in the edge position. That is consistent with the fact we did not reduce the cobalt to metal particles. It just absolutely is rock solid. It stays in there. And if we look at the radial structure function, you can see the cobalt nitrogen is still there, but we've lost this shoulder. And subsequent work after we published this says that this is residual chlorine left over on the cobalt because we used acid to leach away all metal particles. And so we have left behind the cobalt individual atoms. But now high temperature treatments and hydrogen can remove that chlorine. So it's an amazingly sensitive technique to see the local environment around that cobalt. Now look what happens with copper. We tune now to copper, put our material in, and we start heating it up, and oh my goodness, the changes are massive. We see change in the near edge structure, which means we're reducing the copper. That's what we see. This peak goes down up here. The shift down here changes. It's all consistent with copper being reduced to metal. And lo and behold, if we look at the radial structure function on the right, we can see the bonding to the nitrogen is going down and bonding copper going up. So we can actually watch the evolution of copper popping out of those pockets and growing together as a particle as we heat only by a couple of 100 Kelvin. So copper is very, very unstable in these materials relative to cobalt. Okay. All right. Now, back to the original question. How active are these materials? We said they're better than the fuel cell electrodes, right? And then the problem is we don't know how many active sites we have. If we just normalize by all the cobalt or copper in there, could be discounting all of the cobalt and copper that's there doing nothing. Well, while we were doing experiments, we found that when we made acids, they poisoned the catalyst. We said, oh, let's use then poisoning as a way to titrate active sites. So what you're seeing on the x-axis now is putting a poison purposely in the reactor to kill active sites. And so if we don't put any poison in, there's the reactivity. We add a little bit of poison to the cobalt catalyst, it goes down quite a bit. We add just a little bit more, it goes way down. So at the end of the day, very low percentage of this catalyst actually had the active cobalt. So the turnover frequency associated with these sites was 0.24 per second, which is essentially the same as platinum. Copper is just not as active, okay? It's not as stable, not as active, but you can see now where we're going. We have a whole new project working on the fundamental behavior of what is it about these cobalt sites that are now so active in there for these oxidation reactions. So we use selective titration. So at the end of this vignette, we know platinum does oxidation very well. Right? It's been known for decades. We studied it. We looked at the mechanisms of it, but we really wanted to move to look at earth-abundant materials. And so cobalt is much more abundant than platinum, and the small minority of these sites are actually as active as platinum. So it suggests we do have opportunity for serious catalyst design to try to make very, very active non-platinum containing catalysts. So I'd now like to shift gears and say, well, forget oxidizing alcohols to acids. Let's reduce alcohol. So this is another manipulation of oxygen in our biomass resource, right? And so we were thinking about glycerol at the time because of biodiesel formation. This is a molecule that comes out of transesterification of alcohols with fatty oils from seed oils. So if you take platinum, again, there's the world's favorite catalyst, right, is platinum, and in the presence of dihydrogen, you can remove an OH group of this thing, and it removes it at the side, at the end group, right? So you're left with mostly 1,2-propane diol. Okay, I mean, that's okay, but that's not a very valuable molecule. What we really wanted is the di-alcohol 1,3-propane diol, right? This is the one that actually goes on to be used to make Sorona fiber. You can make polymers with this. So 1,2-propanediol, fine. That, like I said, there is a value to it, but this one is actually more valuable. And it turned out that when you add rhenium to the catalyst, you can do the reaction now at significantly lower temperature, and the selectivity shifts down to this thing. It's like, okay, this is very interesting. So we embarked on a study to figure out what in the world is going on so that we can maybe improve the catalyst design. So again, these are now platinum metal clusters. These aren't single atoms like we were just discussing of the cobalt. We're back to platinum metal clusters. These are pretty small. You know, in this example, they were about 1 nanometer in diameter. And then we put rhenium on the surface of it. And we go back to the synchrotron and say, what's the state of the rhenium on this thing? And this is critical to know because this is the thing that changed everything. So we put a bunch of rhenium standards at the synchrotron, and we can see now rhenium 7, rhenium 6, rhenium 4, and rhenium metal. You see there's a big change in this part of the X-ray spectrum, and there's a change in the edge position of when we can excite this core level electron. Okay, so we use that to correlate the oxidation state with that shift in the edge energy. And so we have a nice calibration curve. And when we put in our catalysts, even when we're in hydrogen gas, dihydrogen at reasonable temperatures, reaction temperatures, we always have oxidized rhenium. The rhenium never goes to rhenium metal all the way. Okay, so now we have platinum metal together with some oxidized form of rhenium that makes this magical change, right? So this is counter to what, you know, decades of work in the petroleum refining has shown, right? Because platinum rhenium is essentially the reforming catalyst of the petroleum refinery. But these are high temperature catalysts used with pure hydrocarbons. And they say you can make these alloys, the platinum and rhenium are together, and that's what happens. But we're talking about much lower temperatures with biomass and lots of oxygenates. Totally different case. And so we're trying to do in situ measurement of what the chemical state of the rhenium is by X-ray photoelectron spectroscopy using tunable synchrotron radiation, because now we can depth profile. So now here we have a big platinum particle sitting on the carbon support, and then we impinge X-rays with various energies. And so the outgoing photoelectron will have different energies and therefore mean free paths. So the depth that we're probing into the particle changes as we do the XPS. So this is different from X-ray absorption, which looks at the whole particle. This is now a depth profiling experiment. Okay, so this is a complicated slide, but I'll make it really easy. We can see all the different rhenium species, right? And they're color-coded in these curve fits. But the important one is the blue one, rhenium 0. Okay, in fact, I'll highlight it there with that triangle. Rhenium 0, that's the one that the petroleum refiners see, but we don't. We always see oxidized rhenium. And why? Well, if you do the depth profiling on the particle, the rhenium 0 is definitely there, but it's inside the particle. At the surface of the particle, where you're the most surface sensitive, the rhenium is all oxidized. All right? So under the conditions of pre-treatment and even at flowing dihydrogen at 0.3 millibar, so these are in situ hydrogen experiments, we know there's rhenium that's partially oxidized, which gives you a whole new way of thinking about these materials, okay? Because if you put an OH group with the rhenium on top of platinum, so this is some model structure that was done by density functional theory. So here's a platinum metal particle with a rhenium atom with an OH group associated with that rhenium atom. And so our colleague at the time, Matt Neurock, who's now at the University of Minnesota, calculated the deprotonation energy of this hydroxyl group. What does that do? That just tells you how strong of an acid it is. So if you put an OH group on pure platinum, these things will give you something that's essentially a non-acid material. It's not acidic. But if you put an OH group associated with rhenium on the platinum, oh my goodness, look at where this deprotonation energy is. It's up in the range of what's even known as superacids. So this is now, by having an oxidized rhenium on the platinum, we have evidence of acid formation somewhere between the acidity of a zeolite and a heteropolyacid. So these are strong acids. So that means the mechanism is probably totally different now. So our thought was, we have an acid made in the presence of rhenium in situ. It does dehydration using carbocation chemistry, which is why it comes off in the middle. The secondary carbocation is more stable. It leaves behind an olefin, which we can do enol, keto-enol tautomerization, essentially, is what this is related to, right? So we have the enol, and then it goes to the, in this case, an aldehyde. And then in the presence of platinum and hydrogen, that's going to rapidly hydrogenate. So that was the hypothesis now, is we've added a new catalytic functionality by adding the rhenium, and it changes the mechanism totally. So does it really occur? So we did a lot of exploration. First, is there an acid there? So we had to go find this, okay? So we used infrared spectroscopy of a probe molecule, in this case pyridine, and we could interrogate the bands associated with this, and if there's an acid there to make pyridinium, it should show up by infrared spectroscopy, and lo and behold, it does. Platinum on silica, there's the weakly held pyridine in blue, and then you put rhenium on there and make sure there's no residual rhenium, only the rhenium that's reduced and can't be removed. You see evidence of Bronsted. B is the Bronsted site. So we now have evidence of this, and we did acid probe reactions to confirm that these are catalytically active acids, and they are. Okay, and that's it, written in this paper. So now we know that that site does exist. We explored the acid catalyzed step by deuterating our molecules, just like we talked about earlier. Put deuterium instead of hydrogen along the molecule, and we do see a kinetic isotope effect that's completely consistent now with CH bond activation, okay, which is important for this. So if you think about it, the net reaction is addition of hydrogen to remove carbon and oxygen bonding, right? Yet we see CH is critical. So that is completely consistent with the idea now that an acid is involved and CH bond breaking is critical. And that's the dehydration route to make that what we think is an intermediate olefin, and then we get facile tautomerization and then quick reduction. So we think this is going on, and our kinetics are completely consistent with an acid catalyzed step. And is hydrogenation fast? Well, we tested it, okay? So I won't go over this in detail, but we measured, here's methyl vinyl ketone, and oxygenate with a carbon-carbon double bond. Turnover rates are extremely fast on these materials. Carbon double bond to oxygen can also happen, but it happens better with the interface with the rhenium. So at the end, we now have evidence that this reaction goes through a two-step sequence, but the intermediate, we never see it, which always causes consternation when I talk about this. It's like, oh, wait a minute, you don't see the intermediate. But all the evidence of the hydrogenation of these species suggests that it's much, much faster than the overall reaction. So we're limited by getting to this unsaturated intermediate. All right, so what did we conclude out of this? First, catalyst design by adding these other metals is totally different dealing with biomass, right, than it does with petroleum, because there's so much oxygen around. And so now, even though platinum rhenium is important for hydrocarbon reforming at high temperatures, it's a totally different type of material dealing with biomass. Okay, and we think we now have good evidence they're Bronsted acid sites. We did a bunch of follow-up tests I'm not talking about. Poisoning with a base shuts all down the selectivity, other kinetic isotope effects, reaction orders. But everything's consistent with the idea that this is now a tandem reaction, okay? And so biomass conversion from one molecule to another is going through multiple intermediates. And so the final example I just want to go through quickly is now once we have, we're going back to the acids that we made from alcohol oxidation and now reducing those in dihydrogen. So we still have, this is a reductive process, a little bit similar to what I just went through, but we're actually going from an acid to an alcohol rather than an alcohol to more of a hydrocarbon. Again, this is important for using fatty acids and other acids coming from biomass. Now, we're going to do this with short chain acids to alcohols just because it's a fundamental study. We wanted to get to the gas phase so we could do good kinetics. So the take-home message, it's the rate for acid reduction is positive order in H2 is essentially 0 order in acid, okay, which is going to be important. And here we're taking propionic acid, a C3 acid, to an aldehyde and then an alcohol. And so when there's palladium together with rhenium, we get this. Rhenium by itself is actually terrible unless we heat it to really, really high temperatures. And then, you only see the aldehyde, the intermediate. What does the catalyst look like? This is just a big wide shot that shows that the palladium and the rhenium are all over the place. Okay. Now, here's the issue that we have to think about. The temperature of the reaction is right here in this blue box. And what I'm showing here is the TCD signal when we try to reduce the catalyst. So we put the metal catalysts in the reactor. If we put palladium in there, it takes up hydrogen and reduces the palladium metal. And so in the reaction regime, we try to run the reaction, nothing happens. Okay, we get no reduction of the acid with palladium. You put rhenium by itself in the reactor, you heat it up in the reaction regime, nothing has happened to the rhenium. It's dead. It's terrible. You have to go way up here to change the state of the rhenium and then come back down to the reaction regime, and then it'll work. But if you put the two metals together, the palladium helps reduce the rhenium. So they work synergistically. I hate that word, but that's what happens, is they work together. And now you can do this reaction at low temperature. Again, so what's the state of the rhenium? We go back to the synchrotron. We measure all of this in the presence of acid and hydrogen. So we've done a lot of synchrotron studies in our lab. And here's where the state of the rhenium is in this system, the palladium promoted rhenium oxygen system. And so the rhenium is all oxidized. We don't have any evidence of metal in this case. Okay. Now, this reaction is clearly a tandem reaction simply because we see the propanol, right? At low conversion of propionic acid, here it's what, about 1% conversion. It has a selectivity to, almost 40% to the alcohol. So the rest is the aldehyde. Okay. And by 10% conversion of acid, you can see the bimetallic material is over 80% selective to the final product. So here is it is a true A goes to B goes to C reaction. All right. How many active sites are on this again? So we're thinking all of this is all related to what is active in this stuff, right? This is the problem with catalysis on these complex materials. How much activity is associated with the metals on the surface? So I just want to show you for a few minutes, and then we'll end, a technique we love to use in our lab, which is a reactant switch, either with isotopes or different chain lengths, to measure a transient. So in this case, we're doing C3 acid to alcohol and switch to C4 acid, or vice versa. And we can measure the transient decay of the product and the growth in of the other product. And these decays can be used to calculate the mean residence time of intermediates on the surface, and we can go ahead and back out a turnover frequency by just inverting that first order decay constant. And we can calculate the number of reactive intermediates leading to product. Okay, so transient experiments we love to do. And in this case, we did it on two different catalysts, palladium on silica, palladium on titania. This says the selectivity is the same. The rates are slightly different on the two catalysts, but the selectivities are identical. So we tested these two. And there are the results. So we switch here from propionic to butyric acid, watch the changes in the product distribution with time, and you can see, wait a minute, everything goes down really rapidly on titania, and then this long transient comes out on the one with silica. And that caused us a lot of consternation. But we figured out what it was. The silica is interacting with the alcohol and holds it all in there. So forget the silica results. We figured it all out. I'm not going to talk about it. But what I want you to see is in this step change, here are the decays of the alcohols and the aldehydes, and they're very rapid, okay, in the order of a few minutes. But if you integrate the area under these products, you find out that the number of adsorbed intermediates at this state is only 1% of the rhenium. It's like, oh my goodness, we're back in the same boat. That here we've got this complex mixture of metal oxides on the surface, but on a zero order reaction where we know we're down there and we've got a lot of intermediate, we do a switch and we count everything that comes off at the steady state, almost very little of the rhenium is being used. So again, my colleague Matt Nurok at the time was doing calculations, and we just published this earlier this year, is looking at the mechanism of how this works. And the model had to be such that palladium and rhenium were next to each other. And we have the acid going down, and you can see that what we're showing here is the palladium in blue and the rhenium component is in red, but showing the different components that they have to be kind of next to each other, it looks like, right? And he calculated two different paths about where you have to hydrogenate first and then dehydrate. And so we have all the energetics all worked out of which path is favorable. But at the end of the day, the question now becomes, it's pretty clear that rhenium component is doing the dehydration, just like I told you earlier for our work with glycerol. That rhenium oxide is doing kind of either Lewis acid or even Bronsted acid based dehydration reactions, and the metal is doing the hydrogenation dehydrogenations. The problem is we don't know how close these things have to be on the surface, okay? The fact is that we only are seeing 1% of the rhenium actually participating in the turnover. So I hope, just want to finish up by kind of giving you the big picture of what all these things point toward, right? So early on, we were looking at earth-abundant materials, right? And changing the environment around these earth-abundant materials, it's quite likely we can make stable catalysts that are non-precious metal alternatives. And our example was alcohol oxidation, but we're expanding that right now in the lab. The second vignette I told you about is that really we have bifunctionality, okay? Meaning that thinking that we're seeing only one function of a catalyst when you have these complex metals and metal oxides, really they're actually doing tandem reactions. Even if you don't see the intermediate, it really looks like there's different functionality associated with the different components. And in the second case with the glycerol reduction, it was bifunctional in that it was acid catalyzed dehydration. In fact, we saw that in both the platinum and the palladium rhenium catalyst. But at the end, this is really the highlight, really probing the active sites. In one case, we poisoned active sites. Another case, we used transient kinetics. But in both cases, the fraction of the metal utilization appears to be pretty low. And that reveals potential opportunities for major improvements if we can use atomically precise catalyst synthesis. So now the material science and nanotechnology plays a role, and if we can precisely put things where we want them to be to reach the chemical states that we need for the communication between these sites. And that's essentially what we're working on right now in the lab. So with that, I'd like to acknowledge substantial funding over a decade with our Center for Renewable Chemicals, and also we've had a decade's worth of funding in the related area from the Department of Energy, and of course imaging from Oak Ridge National Lab and synchrotron work at Brookhaven National Lab, and our collaborators and students that were involved in the projects I just spoke about. So with that, I'd like to end my presentation and be happy to address any questions you might have.
Thank you very much, Professor Daves. Very interesting and very comprehensive talk. Very, very, very interesting. We do have a few questions here. Gustavo with us now. I don't know if you can see him, but he just...
Hello, Gustavo.
Hello, Bob. How are you?
Great to see you.
Great to see you too. Very impressive work. Congratulations. Extremely beautiful. Very, very nice. I enjoyed very much your talk.
Thank you. Thank you very much.
And I do have 3 questions, if I may, Savio would allow me to. But go ahead, ask the questions that you have in the chat field if you prefer.
Let's do like this. Let me address the ones that I have here, then I'll hand to you. One of the things, Professor Daves, just a small comment before we go to the questions. As you went through your presentation and I was following, and then I got myself thinking how at the end of the day everything goes to we are all stardust, if you know what I mean, because everything is all about chemical elements and how these things get transformed. It's so magical. I have to say that.
I love the chemistry. The chemistry is a lot of fun.
Okay. So the first question we have here is, it goes related with the catalyst, the platinum and uranium catalyst. One of the colleagues is asking whether did the metal precursor in the platinum uranium catalyst show to be important on the oxidation state of the rhenium outer layer? And if the answer is yes, it's interesting if you could say something about how the mechanism of reduction can be tuned to achieve results that are consistent.
It's a great question, and I don't think I have the answer because I think we always use the same precursor. I'm trying to remember what it was. It might have been ammonium perrhenate or something like that. I can't remember what our exact precursor was. So we didn't vary it. But I do want to emphasize the complexity of this experiment because this infrared experiment taught us a lot. So when you put this precursor on the support with the platinum, if it doesn't reduce, it stays rhenium-7, it will actually come off in water. Remember, we were doing experiments in water, and rhenium-7 is soluble in water. And so you can wash it all off. And when we were starting in this, we didn't know what we were doing, right? So we were at a synchrotron and we had a cell and we're pumping high pressure water through the cell before we had the hydrogen over it. And we watched our rhenium signal disappear right before our eyes. We ended up actually washing all of it out of the system. And so the key is you have to have reduced rhenium or it will dissolve right off of the support. So we had to develop totally air-free handling methods to do this experiment. And we actually washed the catalyst air-free to remove any unreduced rhenium-7 that would show up as an acid on the support. So the complexity of what we had to do post-impregnation was pretty high. So I don't know what the effect of the precursor would be if we have to still do all of these manipulations to make sure we didn't have spectator rhenium that would then just go dissolve into the solution. So if you read a lot of the literature, they take rhenium catalyst in the air, which we now know go all the way to rhenium-7 because of air. And if you put it in water, it all dissolves off, but then it comes back on under these hydrogenolysis conditions. So there's a lot of movement unless you handle it air-free under reducing conditions before you put the water in. And that's what we did, and we published on that.
Yeah. Well, there's another question here, which comes from the undergrad coordinator. So he says like something like that. He thank you for the nice talk, and he says that at the moment we are starting to review our chemical engineering course. I mean, on the undergrad level. And then he wants to know, in your opinion, on terms of the multi-interdisciplinary approach, actually, how you see the multi-interdisciplinary approach in the curriculum contents?
Oh boy, you ask a great question. Okay, you realize I co-authored a book in chemical reaction engineering that I teach from. Mark Davis, my brother at Caltech, and I wrote a book on this. And so there we based it on Gustavo and I's PhD advisor is Michel Boudard, who's no longer with us, but his teachings we brought it down to the undergraduate level related to catalysis and adsorption and transport of involved in catalytic reactions. So in that respect, I mean, we've kind of already written an undergrad-oriented textbook for the chemical reaction engineering course that involves some of this. But yeah, I would say, obviously, my preference is to do a lot of material science. So there's a lot of materials related to chemistry and the engineering. And so at the undergraduate level, I think really, like I said, I think we wrote what we wanted to put in for the undergrads, because the undergrad curriculum in chemistry is pretty packed right now. So it's pretty hard to put as much as we want in.
Yeah, absolutely. Yeah. Another question, it goes like this. It comes from the chemical system engineering department. And then Professor Filete, she puts in a statement where she says that in chemical processes, they are deterministic by nature. But then she wants to know, in your opinion, how the artificial intelligence will play a role on these processes in the future.
Oh, I really don't know enough about it to even venture a speculation. I mean, we've hired new people in our department, actually, a new professor who's doing a lot of machine learning, but that's not artificial intelligence. So machine learning is just is parameterization and optimization and trying to predict. But AI is a totally different field that I don't have enough to be smart enough to even say. Sorry.
Yeah, that's okay. Yeah. Gustavo, do you want to drop your question?
Yes. Thank you, Savio. Let me go to your first experiment that you showed on the cobalt on carbon. You said first it was activated carbon, but you also said it could be graphene, right? And it substituted nitrogen. With nitrogen substituted carbon surface where you put the cobalt in. And that reaction was the oxidation reaction. And do you know what is the state of the oxygen there? Is it O2 or is it O?
Oh, Gustavo, you're discussing right now what we're trying to study in our lab. So,
okay.
So this work has been extended with a new NSF grant, and we're studying gas phase alcohol oxidations as well as CO oxidation. And these things this cobalt catalyst is unbelievably active, okay, for CO oxidation. But the kinetics are totally different from metal particles. Okay, so at this point, we don't know how the oxygen is activated on a single atom. That really bothers us, right? But the kinetics are so fast. In fact, there was a recent paper, I think it was an ACS catalysis by another group that had two different elements with the cobalt in there, and they were running it at dry ice acetone at 100% conversion for CO oxidation. I mean, we have all kinds of problems doing it that cold, but we do it at 0 degrees C, and it's so fast we have trouble getting the conversion down to where we can do stuff. So how is the oxygen being activated? Well, we're doing CO oxidation, which means there's one oxygen going there, right? So what's going on with the other oxygen? So,
and the reason why I'm asking this is because you showed the iron catalyst where you have the iron substituted in the middle of 4 nitrogen atoms that are attached to the carbon atoms, right?
Right.
And that sort of reminded me of the heme in blood, in the red blood cells. And in that heme, what you have is the oxygen molecule. You don't have the oxygen atom there. Right. And the heme is just a carrier for oxygen. And I thought, because you have the nitrogen attached to the carbon, attached to the metal, why you're going to have the oxygen atom instead of the oxygen molecule? Because otherwise you can oxidize the metal, but if you deliver the oxygen molecule straight to the other molecule, like say CO or the alcohol, whatever, Then the molecule, the oxygen molecule, reacts with the other molecule, and God knows where the other one goes. The other atom, the oxygen atom, goes. So that's what occurred to me. So, okay, that question, you asked that question yourself. So, okay, very good.
Yeah,
okay,
okay. Right now, our speculation is that nitrogen is not so innocent sitting there, right? If
I didn't expect them to be.
Yeah, so some people would say, oh, well, it's just stabilizing that isolated atom. But maybe if the chemists, when they make their complexes with these porphyrins and so on, it's non-innocent, right? The environment out through the nitrogen and maybe even beyond is involved in that cycle. So some people have drawn for the alcohol oxidation that you can't dissociate the oxygen by itself. There's no scrambling. You actually have to have the other molecule nearby, maybe associated with nitrogen, and that it's a concerted event.
Okay.
Is that true? I don't know. The DFT folks are working on that with us to try to figure that out.
Then in the other reaction where you show the role of the rhenium, and you said that you have close. How close are the sites for the reaction to take place? How close should be the sites? Because one thing is you are going to have a tandem reaction. You could have one site here and another site very far away, and I mean in terms of molecular dimensions, atom dimensions, but you still could have the reaction. Now,
yes, true.
But do you need to have very close? I would expect them to have them very close by.
Well, that's the nature of our current proposal to the Department of Energy, is to intelligently space these apart and see the effect on reactivity.
Okay.
The problem we had is that in the past, without the transient experiment, we just always normalized rates by how much material there was. But now that we can see how many intermediates are there, we want to try to track how many, the change in intermediates now as we intelligently space the different components. The fact that we only had 1% of the rhenium showing up as doing something, at least with the intermediates that made product in the transient, suggests that maybe you have to be really close. Now, when Matt Neurock was doing the density functional theory work on this, he really had trouble having completing the entire cycle without hydrogen coming from the metal. Now, whether it can spill over or not, I mean, this works on silica, right? I mean, so which should be a terrible catalyst for spillover, but titania.
Well, but you have water in your system, don't you?
Yes. So
and water, water helps water spill over. Yeah. Okay. And the other thing is that in the other experiments where you have the acids and you said it was a zero order, and that's basically a strong adsorption, right?
That's right.
A strong adsorption. Okay.
That's right.
Thank you very much, Bob. I really enjoyed your talk.
Thank you very much. Appreciate
Congratulations. Very beautiful.
Thank you, Gustavo. I have actually one question. It might well be a silly question, which I apologize beforehand. When we were discussing through your presentation the oxidation route, then you made some trials with copper, iron, and cobalt. But then when you started talking about the reduction, then we were playing rhenium. And that was it. And then I was wondering whether there's any other candidate that you can explore as well in the reduction route in order to have a catalyst that's maybe more stable and with a better yield.
Yes, absolutely. So that's a great question. And the background of this has to come from, there was a lot of work by a Japanese researcher named Tomoshiga. And he did a lot of screening with a lot of the metal oxides, and the rhenium turned out to be really good, but it wasn't the only one that worked. Others did. I think molybdenum works fine. Tungsten works fine. So we had so many problems with rhenium that so many different oxidation states show up. It's the high valent rhenium is water soluble, so it comes off, and So our future work now is actually leaving rhenium gone, and we are focusing on the tungsten oxide system. Much more stable. We could control things a lot better, much fewer accessible oxidation states under these chemical potentials. So that's a great question. We started with it because the screening work that was done a decade ago showed rhenium was really good at this. And so we usually start with what looks to be the best and then try to understand it. And then we realized all the problems later. And so, but that's a great question. Yeah. I would not advocate going any more with the rhenium right now, to be honest with you. It is so hard. Yeah. In fact, we were doing liquid phase acids for a while, right? I had a graduate student spend a couple of years doing heavy, acids produced biologically, which are all liquid phase, and we kept leaching all the rhenium. It kept going in the reactor, and it was tough to work with, which is why we ended up moving to vapor phase to do the kinetics, and then now we're working with tungsten, which works quite well.
Another question that I have, maybe the last one. We've seen in terms of biosystems, lots of, let's put this way, lots of reactions where the quantum tunneling plays a very important role, and it seems that the nature somehow goes that way. And then I wonder, in terms of the catalysts that you are working and exploring and doing research, how the quantum tunneling and molecular computational modeling, things like that, can help, and what kind of role they can play to enhance the quality, if I may say, of the catalysts?
Well, we are trying to team up with an electronic structure person on almost everything right now. So we hired a new faculty member in my department because our collaborator on all this work I mentioned moved to Minnesota. So we hired a new assistant professor named Chris Palucci, and he's working together with my students on computing these single atoms in the nitrogen doped, carbon materials, because we're trying to understand, maybe it's not the fourfold, maybe it's a defect site, or it's on the edge of a carbon that's important. So we can do a lot of probes computationally that we can't access experimentally, right? And so it's really important to understand what makes energetic sense in our hypotheses if we're ever going to make any headway on the synthesis. So the DFT calculations are absolutely critical. Now, he's actually looking at the slide right now, and Gustavo's question about the spacing of the components, he's actually working with us now on trying to understand the spillover between a metal and metal oxide and the hydrogen potentials. And, will tunneling play a role? Tunneling tends to be more important with the small thing like hydrogen atom, right? So that is really critical, we think, to understanding what's happening if we have molecules as hydrogen shuttles, or if we're, translating across a surface. We can measure things, but to have the DFT complementarity will really help us understand, how close these sites really need to be, if at all, right?
And it may help you as well to save a lot of time, because you can go and play with the computer. And
yes.
If the things are not looking good, then you just give up and go to something else. Yeah.
Yes, absolutely.
Yeah. Okay. So it's 9 minutes after 2 o'clock. So I think we're starting to running late, and I would like to take.
Savio?
Yes.
I have an extra question for Bob. It is more a technical question. You showed some catalysts with the titanium, titanium oxide, and before the reaction, you reduced the catalyst.
Yeah, but we try not to go really high temperature to avoid.
Okay, yeah, that was my question. Okay.
Yeah.
So to avoid
yes, MSI
+3. Yeah. Okay.
Yeah, so
okay.
I mean,
I didn't remember seeing the reduction temperature prior to reaction. So
yeah, it's a couple hundred degrees C. So when we looked at, here it is on silica, the fact that you could put the bimetallic and get the rhenium to reduce at low temperature allowed us to avoid the SMSI. Okay, but you're right. If we did it at high temperature, we'd have a whole nother complication. Yeah. In fact, others have used that SMSI as part of the catalyst component itself.
Exactly, because you're going to have some titanium-3 there,
Yes.
and that's going to introduce some extra state.
That's exactly right.
Okay, thanks.
Yep.
Thank you.
Mm-hmm.
Okay, so before we go, I need to say one thing to you, Professor Daves. Gustavo's department has the best coffee in the School of Chemical Engineers. So as soon as we get rid of this pandemic breakout, you should come over and take a cup of coffee. I'm sure you enjoy to have you here.
Oh, that would be wonderful. You know, I have to say that Gustavo was the best coffee maker in graduate school when we were grad students. You know, he was famous for making the coffee every day. So he's clearly at the right place.
Yeah. So maybe that's the reason why his department has the best coffee. Okay. So with that, I would like to thank you so much for accepting our invitation. It was very nice to have you on board. There's loads of questions here, but unfortunately, we don't have the time to go through all of them. Yeah, thank you very much. It was
all right. Thank you, Savio.
Thank you.
Appreciate it.
Thank you,
right.
Bob. Thank you.
Have a nice day.
You
too.
And bye for now.